Hello everyone, I'm here to talk to you today about the Doppler effect. And maybe you've lived in a cave your entire life and you've never heard the Doppler effect, but this is what it sounds like. Wee-oo, 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 wee-oo. You know that sound you get when something like an ambulance drives by, and it sounds really high-pitched when it's coming towards you, and it sounds really low-pitched when it's going away from you. That's called the Doppler effect. It was kind of described by this guy Doppler, and it kind of hinges on a couple of ideas. The first one is a bit of a review for you, that you need to understand frequency. What we describe in physics as frequency. In real life, we kind of hear that with sound as pitch. Higher sounds like, oh, very high, that's a high frequency, and low sounds, low, that's a low frequency. So if we keep that in mind, we can figure out why it is this ambulance is going to make a high frequency when it's coming towards you, and why it makes a low frequency when it's traveling away from you. There's a little animation here from the guys at the University of Virginia that might help you understand this. So here we've got a little dot. This dot is going to represent our ambulance. And when I start it going, you notice that it's going to make these nice little sound waves. And right now it says it's making 2 every second. It's got a frequency of 2. And I've got this microphone here. I can put it up. You can actually hear the sound waves. 2 of them every second. Now this is called the source. This ambulance, this red dot, is our source. Now what we're going to do is we're going to take our microphone, put it over there, and we're going to make the source move. Watch what happens when I get it going. Now the source is actually starting to catch up to those sound waves it is producing. They're getting a lot closer together. They're getting scrunched together. Now listen to what happens when the microphone comes in contact. Oh, listen to that, okay? We had that microphone picking up all of those compressed sound waves. The frequency was much, much higher, and then much lower, which means that the pitch here is going to be much higher than the pitch here because the frequency is different. Now, how can we describe this higher frequency and this lower frequency? Well, Doppler came up with an equation that would allow us to describe that. It's kind of an ugly looking one. It looks like this. Frequency is equal to the speed. This is the speed of sound in air. We just call it in our physics textbook here v. The speed of sound in air divided by that same number, that exact same v, the speed of sound in air, plus or minus the velocity of the source. This is like the speed of the ambulance, okay? And that's all multiplied by the frequency of the source, measured in hertz. Speeds could be in kilometers per hour, meters per second. It doesn't make much of a difference. We'll stick them in meters per second. That usually seems a little safer. Now, this is like 2 equations in one. We've got a plus or minus in there. What the heck is that plus and minus for? It's there because when the ambulance or whatever the source of the sound is coming towards you, you're going to use the subtraction sign. You're going to put in there a minus sign, okay? And you're going to ignore the plus, and you're going to subtract the velocities in the bottom. And when it's coming away from you, when it's going away from you, you're going to use the plus sign, and then you're going to ignore the minus sign. I'll show you a little example here. A police car has a horn with a frequency of 220 hertz. This is the frequency when it's not moving, what it would normally sound like. The speed of sound is 340 meters per second, and the car is moving at 120 kilometers per hour. What's the perceived frequency? That's the frequency you hear of the horn when it's moving towards you, when it's moving away from you. Okay, first thing we want to do, 120 kilometers per hour, we want to make that into meters per second because we have 2 different units there, so we don't want to compare different units. I'll divide that by 3.6. That's my conversion factor. 33.3 repeating meters per second. Okay, now for the formula. First, I'm going to do A. I'm going to do car moving towards me. That means I'm going to be using the equation which has a minus sign in there. Okay, so I'll just put that minus sign in so I don't forget. Now, the first v in the top here, that's the speed of sound. So 340 meters per second. The second v here is the same as the first. They're just v. So that's 340 meters per second. And vs is the speed of sound, 33.3 repeating meters per second. That's all multiplied by the frequency of the sound, which is 220 hertz. Now, if you think about this fraction, it should make sense to you. We're taking, in the denominator, a smaller number than 340, The numerator is a bigger number. Well, it is 340. So a big divided by a small number is going to end up with a whole number. So, something greater than 1. So when I times it by 220, it's going to give me a frequency that's bigger than 220 hertz. It should get larger, which is what we're expecting, because we know when this thing comes towards us, we know that it is going to be having a higher frequency. So plug and chug. That's probably good for my decimals. And that should work out. Nope, calculated it wrong. Throw in another set of brackets. Or do it like this. Times 220. There we go. So 243, oh no, I did it the same, that's good. Yeah, 243 meters, or hertz. Sorry, meters per second. Hertz. That's my frequency when it is going towards me. I used the minus sign in the expression. Now that I have that typed in my calculator, going away from me is dead easy. This is the cool thing about it. Look, you got your calculator, you bring that calculation back up. The only difference is I'm going to change it from minus to plus. Boom, boom. So there we have it. Our frequency now, oh wow, this is not being multiplied by 220. There we go. 200. 200 hertz when it's moving away from you, which makes sense, right? Higher frequency when it's moving towards you, it's louder. Lower frequency when it's moving away from you, it's not louder, it's higher pitched. When it's moving away from you, lower pitched. So that's the Doppler effect. For more information, there's a nice package of notes on my website at ldindustries.ca.